Welcome to the Deep Dive. Today, we're embarking on a really fascinating exploration. We're going right into the heart of quantum mechanics and, the very fabric of reality itself.
Sounds ambitious.
It is. Our guide, our sort of compass for this journey, is John Gribbin's 1995 book, Schrödinger's Kittens and the Search for Reality. It's subtitled Solving the Quantum Mysteries.
A classic, even now.
Absolutely. And our mission here is basically to navigate Gribbin's, his comprehensive update on quantum weirdness from back then. We want to pull out the most surprising bits, the really crucial takeaways, to give you a shortcut, sort of, to understanding these, let's face it, pretty profound scientific and philosophical debates.
Right, and maybe let's clarify something right at the start. The kittens in that title,
Oh, yeah, good.
they're not actual cats, thankfully.
No cats were harmed.
Exactly. Gribbin uses kittens as a metaphor, really. They stand for these smaller-scale, testable quantum paradoxes. So we're talking about things like single photons or individual electrons, maybe atoms. Stuff that physicists could and can actually manipulate directly in the lab. And that lets them measure phenomena like superposition.
That's where a particle is in multiple states at once.
Precisely. And entanglement, the spooky action at a distance where particles stay linked. And also decoherence. That's the process where quantum states kind of lose their quantum nature when they interact with the environment.
Okay, that makes sense. So think of this deep dive maybe as a kind of scientific detective story. Gribbin sort of sets his book up that way too. We'll first revisit the initial mystery, quantum reality, what is it? Then we look at the new evidence, the experiments that revealed some really bizarre truths.
The plot thickens.
Exactly. Then we meet the competing interpretations, our suspects, if you like, each one trying to solve the puzzle. And finally, we'll look at the bigger picture, the implications for physics, for the cosmos. So, yeah, let's start unpacking this.
Well, it's worth remembering, when Gribbin wrote Schrödinger's Kittens back in '95, it was actually a follow-up. He'd written In Search of Schrödinger's Cat in 1984.
Right.
So this was his decade-later update. His goal was to bring in all the latest experimental results, confirming, just how strange quantum mechanics really is, plus new theories tackling the measurement problem, that big headache in quantum physics, and just a deeper philosophical look at what reality even is. He wasn't just repeating himself, he was building on actual new discoveries, real experimental proof.
That takes us neatly back to Schrödinger's original thought experiment, doesn't it? From 1935. He used that poor cat in the box scenario.
The infamous cat, yeah.
To show just how, absurd the implications of quantum mechanics seemed back then. A cat that's simultaneously alive and dead until you open the box and look.
It was meant as a criticism, really, a reductio ad absurdum. He was highlighting the problem, not suggesting it was really like that.
He wasn't offering a solution.
No, exactly. And that's where Gribbin's kittens come in. They shift us away from the thought experiment, from the hypothetical cat to these real-world kittens, these single quantum things. Photons, electrons.
Things you can actually test.
Right. These tiny scenarios let physicists directly observe stuff like wave function collapse.
Okay, wave function collapse. That's when the particle's fuzzy probability wave settles into one definite state. Like, now it's here, not possibly here or there.
That's the idea, when you measure it. And they could also measure entanglement properly and decoherence. These were just things you couldn't really do experimentally back when Schrödinger first dreamt up his cat paradox.
Okay, so the next big piece Gribbin brings in is really significant. John Bell's 1964 theorem.
Ah, Bell. Yes.
Before Ball, a lot of this was still kind of theoretical, almost philosophical arguing, wasn't it?
It was. People could argue about hidden variables and things.
But Bell's theorem, it mathematically proved something properly disruptive.
It really was.
The key insight, and Gribbin explains this well, is that Bell basically shattered our classical view. He showed the universe cannot be both local.
Meaning influences can't travel faster than light.
Right. And realistic.
Meaning objects have definite properties even before you measure them. Like, the cat is either alive or dead, we just don't know which.
Bell showed you can't have both. Local and realistic. One of them has to go.
And that's the truly startling part. We have to give up one of those fundamental assumptions about how the world works.
Wow.
Yeah. Gribbin lays out Bell's inequalities pretty clearly. Basically, classical physics sets certain limits on how correlated, how linked particles can be if they obey locality and realism. But experiment after experiment showed those limits being broken, violated.
But the real clincher came with Elaine Aspect's experiments. In 81 and 82?
Yes, Aspect's work was groundbreaking. Beautiful experiments. They closed major loopholes that people had pointed out in earlier tests. His work essentially proved it. Nature is non-local.
Meaning particles can affect each other instantly across space, faster than light could get there.
Without any known signal or force connecting them, it's baked into quantum mechanics. This wasn't just philosophy anymore. It was hard experimental fact.
Okay, so if Bell and Aspect gave us the crucial evidence in our detective story, what other experimental breakthroughs from, say, the 70s up to the 90s did Gribbin highlight? You mentioned quantum optics earlier.
Oh, absolutely. There was a real flurry of activity then. Gribbin goes into experiments using entangled photons, showing these correlations that were just, well, impossible under classical rules. Perfect correlations.
Okay.
He also talks about quantum eraser experiments. These are really mind-bending.
How so?
They basically show that even just the possibility of finding out which path a particle took through an apparatus is enough to destroy its wave-like behavior, its interference pattern.
Wait, just the possibility of knowing?
Yeah.
Even if you don't actually look?
Yeah. It's almost as if having the information potentially available retroactively changes the particle's past behavior.
That's deeply weird.
It is. And then you have delayed choice experiments, which sort of push that even further. They suggest that a choice made now about how to measure a particle can affect what you'd say about its state in the past.
Okay, my head hurts slightly now.
Join the club. That's quantum mechanics for you. But the point Gribbin makes is that all these experiments, taken together, they forced the issue. It wasn't just abstract pondering anymore. We had empirical proof. The universe fundamentally does not play by classical rules.
It really is counterintuitive at its core, isn't it? Which raises the next big question for our investigation. If our everyday classical understanding is wrong, how do physicists try to make sense of it all? This must be where Gribbin introduces the suspects, the different interpretations of quantum theory.
Exactly right. Gribbin devotes a good chunk of the book to laying out these different philosophical takes, and he treats them all pretty fairly, I think.
So what are the main contenders?
Well, you've got the Copenhagen Interpretation. This is the sort of traditional view associated with Bohr and Heisenberg. It basically says a particle's properties, its reality, are undefined until you measure it. Then, poof, the wave function collapses into a single outcome.
But it struggles with how that collapse happens,
Right.
The measurement problem.
That's its main difficulty. It doesn't really explain the mechanism of collapse or why observation triggers it. It just says it happens.
Okay, well.
Then there's the many worlds interpretation from Hugh Everett III. This one's quite elegant, in a way. It avoids collapse completely by saying all possible outcomes of a quantum measurement actually happen in separate branching universes. Every quantum choice point splits reality.
Wow, that's a lot of universes.
It is. A mind-bogglingly infinite number. That's the philosophical price you pay, perhaps. No collapse, but infinite parallel worlds.
Okay.
Then you have things like the de Broglie-Bohm pilot wave theory. This suggests particles always have definite positions, but they're guided by a separate pilot wave. It's deterministic, which some people like, and it reproduces quantum predictions. But it's explicitly non-local, which we know reality is anyway, but it feels a bit like adding an extra layer.
Hidden variables, essentially.
Kind of, yeah, but non-local ones. Then there's the transactional interpretation by John Kramer. This one involves quantum events, handshakes happening via waves traveling both forwards and backwards in time.
Backwards in time again.
Yep. Definitely non-intuitive. And finally, there's decoherence. This isn't a full interpretation on its own, maybe, but it's a crucial piece of the puzzle. Decoherence argues that you don't need a conscious observer or even wave function collapse in the Copenhagen sense. Instead, when a quantum system interacts with its environment, air molecules, photons, whatever its quantum coherence, its ability to be in multiple states gets spread out and lost very, very quickly.
So it looks like it collapsed.
Exactly. The quantum weirdness gets diluted into the environment, making the system behave classically for all practical purposes. The secret gets out, you could say.
So it loses its quantum properties because of interaction, not because someone looked.
That's the core idea. Gribbin explores the strengths and weaknesses of all these different viewpoints.
What's really interesting there is how Gribbin handles the role of consciousness, the observer. I gather he's careful not to get too mystical.
Very careful. He steers clear of those mind creates reality claims that sometimes pop up in, less rigorous discussions.
But he still ends up somewhere pretty profound. Does he draw a line between a person looking and, say, a Geiger counter clicking.
He acknowledges that observation, or maybe better put, measurement or interaction, is absolutely central. It seems inseparable from defining what actually happens at the quantum level. But he emphasizes that it's the act of measurement itself, the interaction that forces a definite state, that's critical, not necessarily whether the measuring device has consciousness.
So a detector does the same job as an eyeball, essentially.
In terms of triggering that transition from quantum possibilities to a classical outcome, yes. And this, Gribbin suggests, opens up a really intriguing possibility that maybe reality itself isn't this solid, fixed thing we assume it is. Maybe it's something that emerges from quantum processes, perhaps an emergent property of quantum information being processed.
Well, reality is an emergent property of information.
It certainly challenges our basic intuitions about what existence means.
Okay, so if we zoom out now from these tiny quantum puzzles, how does Gribbin connect all this fundamental weirdness to the bigger picture? To cosmology, maybe?
Yeah, he definitely broadens the scope in the later parts of the book. He shows how these quantum effects aren't just lab curiosities, they have implications on the grandest scales imaginable.
Like where?
Well, black holes, for instance. He talks about Stephen Hawking's work on black hole radiation, which itself relies on quantum effects near the event horizon. It raises questions about whether information is truly lost forever if something falls in, which clashes with quantum principles. He also looks at the universe's beginning. The idea that tiny quantum fluctuations, these unpredictable little quantum jitters in the very early universe, could have been magnified by cosmic inflation. Those tiny fluctuations might be the seeds that eventually grew into all the galaxies and clusters we see today. So quantum mechanics might be written into the very structure of the cosmos.
Amazing.
And he touches on the quest for a unified theory. The search for a theory of everything, particularly quantum gravity. He suggests that finding such a theory, one that unites gravity with the other forces under a quantum framework, might finally solve that persistent measurement problem. It could give us a seamless picture connecting the quantum and classical worlds.
So bringing it all together, what does this mean for us sitting here now? I mean, Schrödinger's Kittens came out in '95, almost 30 years ago.
Yeah.
But it feels like the core message holds stronger than ever. Quantum mechanics just keeps forcing us to rethink everything we thought we knew about reality.
Absolutely.
Gribbin's work, exploring Bell's theorem, the experiments, the different interpretations, even from that mid-90s perspective, it really drives home that our understanding of existence is, well, it's still very much a work in progress.
It's definitely not a closed book. The questions are still profound, the answers still debated.
Yeah.
And perhaps that leaves us with a final thought, something for you, the listener, to really chew on. Given everything we've discussed, given that our understanding of what actually happens down at the quantum level seems so tightly bound up with the act of observation or measurement, whether that's by a conscious mind or just a simple detector, what does that really imply about the fundamental nature of reality itself? And pushing it one step further. If reality could be, as some interpretations suggest, an emergent property arising from how quantum information is processed, how might that fundamentally change how you perceive the world, and indeed how you perceive your own place within it?